Well, let me introduce Dr. Elton Cairns, right? Elton is, I'm going to read this because it's really impressive. Elton is a professor of the Graduate School in Chemical and Biomolecular Engineering at UC Berkeley. He holds the title of Faculty Senior Scientist at Lawrence Berkeley National Laboratory. He's published over 280 papers, has 25 patents, and a book in the area of electrochemical kinetics. Maybe we can get him to define that. Batteries, fuel cells, and more. His current research focuses on sulfur in rechargeable batteries. So please welcome me in welcoming Dr. Cairns.
Thank you very much, Ron. So you've heard a lot about sulfur already. So this is a bit about a specialty application of sulfur. We're interested in using sulfur in batteries. The negative electrode of the battery is lithium, and the positive electrode is sulfur. As you have already seen, sulfur is very common. It's available in large quantities for very low prices. It's environmentally benign, and it's also non-toxic. You can eat sulfur with no harm. Many pharmaceuticals contain sulfur, so it's quite a benign element, and therefore it increases the suitability of batteries that contain sulfur rather than the traditional transition metal oxide materials. So in terms of applications that we would like to fulfill with the lithium sulfur batteries, probably the most popular one and the one that would be of greatest benefit if we are successful in developing a lithium sulfur battery is batteries for electric cars. So here are a couple of examples of electric cars. We have the Nissan Leaf here. It currently has a range of about 80 miles between recharges. If we would replace the lithium-ion battery in the Nissan Leaf with a lithium sulfur battery, we would get a range of more than 300 miles. And the same thing in the Tesla. We could have a much smaller battery than the Tesla battery and still have a range in excess of 300 miles. So this would put electric vehicles powered by batteries on an equal footing with gasoline-powered cars, which typically have a range between 300 and 400 miles. So how do lithium-sulfur batteries compare to the lithium-ion batteries that we're all familiar with? In order to do this comparison, we have done some calculations based on the properties of the lithium and the sulfur. So the lithium sulfur battery can give us 2,600 watt-hours of energy per kilogram of lithium plus sulfur. The lithium-ion batteries that you're familiar with can give us a specific energy of 580 or so watt-hours per kilogram. So this is an advantage of more than a factor of 4. So that means that in your cell phone, you could operate the cell phone 3 or 4 times longer than you do now with a lithium-ion cell before you need to recharge it. The advantage of lithium sulfur on a volumetric basis is not as great as it is on a weight basis. We have 1,800 watt-hours per liter for lithium-ion cells and something approaching 3,000 watt-hours per liter for the lithium sulfur cell. So the advantage is a little less than a factor of 2 in that situation. But a significant advantage is the fact that the materials in the lithium sulfur cell are environmentally benign. Lithium ion cells contain transition metals, among them cobalt and nickel, and both cobalt and nickel have toxic features, and the cobalt is very expensive. Cobalt costs about $20 per kilogram, and sulfur costs less than $0.50 per kilogram. So how does a lithium sulfur cell compare to a lithium ion cell? In the upper part of this slide, we see our lithium ion cell. We have graphite, which acts as a host material for the lithium. So the lithium is held between the layers of the graphite. So all of the carbon of the graphite is just dead weight. The reactive material in the negative electrode is actually the lithium. But the graphite anode is only 10% lithium by weight, and it's 90% carbon. So that's a lot of dead weight. In the positive electrode, we have a transition metal oxide like cobalt oxide or manganese oxide or nickel oxide. All of those are very heavy compared to the lithium. And these transition metal oxides just act as a host for the lithium. So during discharge, the lithium shuttles over to the transition metal oxide and is hosted there between the layers of the oxide material. And then when you recharge the battery, you move the lithium back to its original location in the negative electrode. Now, as we all know, the electrolytes that are used in lithium-ion cells are very flammable. And when you heat up the lithium-ion cell, the transition metal oxides release oxygen. So sealed inside the cell, we have all the makings of a fire. We have the oxygen from the transition metal oxide, and we have the organic flammable solvents in the electrolyte. So the fire can start inside the battery, and then the battery breaks open. It's not the reverse. The battery doesn't break, and then the fire starts. So in our work, we're making changes to all of these elements of the cell. Instead of having a graphite anode, we use pure lithium metal as a negative electrode. We replace the flammable organic solvent-based electrolyte with a safe, non-volatile liquid electrolyte, which is based on ionic liquids, which are non-volatile and non-flammable. And for the positive electrode, we have sulfur as the active ingredient instead of a transition metal oxide. So the lithium is much lighter weight than the graphite, and the sulfur electrode is much lighter weight than the transition metal oxide electrode. So we are saving weight because our electrolyte is non-flammable. That makes the lithium sulfur cell very safe. So we've changed everything in the cell, and we're in the process of trying to make the cell perform in a manner that is commercially attractive. But sulfur does have drawbacks. It has the advantages that we've discussed of being environmentally benign and very lightweight, but unfortunately, sulfur is not an electronic conductor. So we have to provide electronically conductive materials in intimate contact with the sulfur in order to have an electrode. An electrode, by definition, must be electronically conductive in order to carry out the electrochemical reactions. So we mix various forms of carbon in sophisticated ways with the sulfur in order to improve the electronic conductivity. Sulfur also changes volume as we discharge the cell. So we start out with sulfur, we discharge the cell making Li2S, and when we do that, the volume of the Li2S turns out to be much greater than the original volume of the sulfur, so we have about a 78% expansion. So our electrode has to accommodate that mechanical expansion. And we engineer our sulfur so that it is combined with carbon on a nanoscale, and we provide very good electronic conductivity by means of the carbon. And when we make the electrodes, we use an elastomer as a binder to accommodate the volume change. Another difficulty associated with the chemistry of sulfur is that during the discharge reaction you can form polysulfides, which means various numbers of sulfur combined with 2 lithium atoms to make a lithium polysulfide. These lithium polysulfides are soluble in organic solvent-based electrolytes, and that means that the lithium polysulfide can dissolve in the electrolyte and move away from the electrode, and that represents a loss of capacity of the cell. So we use electrolytes which have very low solubility for the polysulfides. So if we build a lithium sulfur cell and we operate it in the laboratory, measuring the voltage of the cell, so you can see it's of the order of 2 volts, versus the capacity of the cell, and here we're expressing that in terms of milliamp hours of charge per gram of sulfur in the electrode, we see 2 regions, an upper plateau where the sulfur is reacting with lithium to form lithium polysulfides, and a lower plateau where the sulfur and the lithium polysulfides react with more lithium to form Li2S. And this is the overall cell reaction up here. And the average cell voltage is about 2.17 volts. So that's what's happening inside the lithium sulfur cell as we operate it. But in order to get that kind of performance, we must very carefully construct the sulfur electrode so that we can utilize all of the sulfur that's in that electrode and get the maximum capacity. So we have found that if we combine on a nanoscale the sulfur with a conductive material, graphene oxide in this case, to form a very thin and uniform coating over the surface of graphene oxide flakes, and then we further protect the sulfur using cetyl trimethylammonium bromide. So these are long carbon chains that adsorb on the surface of the sulfur and protect it from dissolution. This is a scanning electron micrograph that shows the flake-like structure of the graphene oxide, which is covered with the sulfur. And this green area here shows that all of the surface of the graphene oxide has been coated with the sulfur material. So that's what we're looking for. A very highly conductive material on a nanoscale that we can use in making our sulfur electrodes. So we combine our sulfur graphene oxide here with some carbon to give us additional electronic conductivity and a binder. This SBR is styrene butadiene rubber. So it's a rubbery binder that allows the electrode to expand and contract as we charge and discharge the cell. And so in our early work, we used sulfur loadings of about 1 milligram of sulfur per square centimeter of electrode area. And these plots show some of our experimental results. This is the discharge curve, the red curve. And here is the charge curve, the blue curve. And we want these curves to be as close to one another as possible, giving us very high efficiency. Here we show the capacity of the cell as we repeatedly charge and discharge it, and you can see the capacity is very stable over 40 cycles, and we're getting about twice the capacity of an equivalent lithium-ion cell. In this lower plot, we show the very long-term testing out to 1,500 cycles, showing quite good capacity stability. You can see that we are gradually losing capacity in the cell due to minor and slow structural changes in the electrode. But even after 1,500 cycles, we're still getting 700 milliamp hours per gram of sulfur, which is far better than a brand new lithium-ion cell. So the next thing we needed to do in order to have a cell that is commercially interesting is to increase the amount of sulfur in the sulfur electrode. And so these experiments show that as we go up from 0.5 milligram of sulfur per square centimeter to about 2.5 milligrams of sulfur, we get essentially the same utilization of the sulfur. So that's very good news. And these are the discharge curves and these are the charge curves. So that means that the scale up in the loading of the sulfur is very promising for potential commercialization. We asked one of our industrial colleagues to make an estimate of the cost of the materials to make the lithium sulfur cell and compare that to the lithium ion cell. So on the left we see the breakdown of the materials cost for the lithium sulfur cell compared to the breakdown of materials cost for the lithium ion cell. You can see that in the lithium ion cell, the positive electrode is by far the largest cost item. But in the lithium sulfur cell, the positive electrode is by far the lowest cost item in the cell. The separator cost in the lithium ion cell is the same as in the lithium sulfur cell, so that allows you to see that as a percentage, the separator takes up a larger fraction of the total cost, and this is an indicator that the total materials cost for the lithium sulfur cell is much less than that for the lithium ion cell. So we want to move to commercialization, and we are receiving support from a battery company to do that. We've been improving the cell performance using the higher loading sulfur electrodes. We are working toward a practical value of specific energy. In order to get to a specific energy of more than about 300 watt-hours per kilogram, we need to have sulfur loadings that are at least 4 milligrams per square centimeter, and we've already achieved that. We are up above 10 milligrams per square centimeter already. We have increased the sulfur content of our electrodes to more than 70%, and we're still measuring how long the cycle life is with these higher loadings. As we put more and more sulfur into the positive electrode, it takes a longer and longer time to discharge and recharge the cell. So it's going to take us quite a few months to really test the cycle life of our high loading cells. The electrolyte in the cell is just dead weight. It does not contribute any of the energy that is stored in the cell. So we want to minimize the weight of electrolyte in the cell, and we would like to have less than 3 times the weight of electrolyte as compared to the weight of the sulfur in the cell. And this plot shows the importance of increasing the sulfur loading up to more than 4 and maybe as high as 10 milligrams per square centimeter. And it shows the importance of reducing the amount of electrolyte in the cell. We are already in the range of 3 to 4 for electrolyte to sulfur ratios, and we may be able to go even higher. And you can see that reducing the amount of electrolyte really leads to a major increase in the amount of energy that you can store in the cell. So we're working on all of those things now, and we've moved on from coin cells, which are about the size of a nickel or a quarter, to these pouch cells, which are of about the size that would be used in a cell phone. And on the left side you can see the list of the components that are in the cell, and it's about 25 square centimeters. And more recently we've been building pouch cells that are as large as 35 square centimeters. So we think that the lithium sulfur cell is a very strong candidate for the next generation of batteries after the lithium ion cells. There are difficulties in using sulfur, and I've already discussed those difficulties, and we think we've overcome them pretty well. And the sulfur graphene oxide electrode has already demonstrated very good performance, very high rate capability at low loadings, and very long cycle life. So we think this is quite a promising technology. And I'd like to show you the members of our group. And much of the current work is being done by Dr. Yun Hua, shown here with his wife and son. And the predecessor to Dr. Yun Hua was Dr. Min-Kyu Song, who is now a professor at Washington State University. And I'd like to acknowledge the support that we've received from these organizations over the last several years. And I'd like to thank you for your attention.
Thank you, Dr. Cairns. Let's see if we have any questions. Do we have a microphone? We do have a microphone. Does anyone have a question? I personally have a Volt, and I would love to have one of these batteries in my Volt.
I actually had a question about the, I don't have it written down. The Alberta pyramid, if someone were to set that on fire, how long would that burn for? And if it turned molten, how much land would it cover?
I have no idea. That's a great question, but I have no idea. That would be, first we'd have to know how big the pyramids actually are. And when I called up the oil company, they were hesitant to give me any actual facts and figures. I don't know why. But I think they're being sued by virtually everybody in the world, so they were a little skittish. The oil sands are fairly controversial. So, any other questions? This question right here, Melissa.
So you have this battery in the lab, and you've worked it all out, and now you're going into kind of a manufacturing model. What's the trajectory? How many years to get this new sulfur battery in my car?
Well, as you can imagine, the amount of time it takes to really commercialize this technology or any other technology depends on the investment that you make in terms of the people power to create the technology necessary for manufacturing the battery. So we're working in partnership with a small battery company now, and we are transferring the technology by means of writing reports to the company. We have a person, an employee of the company working together with us in our labs, and he is the person who is actually building the pouch cells that I showed the photograph of. Then he, next year, will move to his company and figure out what techniques are needed for manufacturing this cell on a volume basis. But a lot of the procedures that are used are quite similar to the procedures that are now being used to make lithium-ion batteries, so the manufacturing equipment will also be quite similar. And my guess as to the amount of time from here to commercialization would be somewhere between 3 and 5 years if the appropriate investments are made.
And what would an appropriate investment, like what would it cost to retool the, or not, you wouldn't have to completely retool, obviously, similar tools, but how many millions?
That's a good question. Most new technologies take not millions but billions. Your car costs the auto company billions of dollars to go into production on. So I would say that in the case, since the lithium-ion battery business is already well established, to convert from the equipment from lithium-ion to lithium-sulfur would take a lot less money than if you had to start from scratch. So I would say it's probably in the range of, to get pilot quantities, tens of millions of dollars, and to get up to full-scale production for, say, a Chevrolet, would be a couple $100 million.
So I have a question. Cars are an obvious application, but there's a lot of people who are putting solar cells on their homes, and those don't work at night. So if you want to be completely off the grid, you have to have some way to store energy in your home. And it's very attractive to have a battery that is not going to burn your house down. Is this another application that you're looking at?
Yes, I think it's a very good application. As you may know, Tesla is offering their batteries for homeowners now, but I question the safety of those batteries. The lithium sulfur battery is much safer and it should be much less expensive, so I think for stationary energy storage, such as in homes, it would be a very good candidate.
Do we have another? Oh, there's another question over here.
How competitive is this whole process of battery development? I mean, 5 years, somebody else could come up with something that would be to eclipse even this. I mean, how fast is this technology moving?
Yeah, that's a very good question. The whole battery business is highly competitive, both for mobile applications and stationary applications. And there is a large number of chemistries that have been proposed and investigated, but not many chemistries have reached commercial success. And of course, we're limited by the elements on the periodic chart, and there are only a couple elements that can give us more energy than lithium sulfur, and those are lithium and oxygen and lithium and fluorine. And as you may know, fluorine is very dangerous, and there are not many materials that are stable in the presence of fluorine, and it's a gas, therefore difficult to store. So nobody, to my knowledge, is working on a lithium fluorine battery, but there is a lot of research going on now on lithium oxygen, and that has turned out to be a very difficult system to develop. So I think if it ever does get developed, it's about 30 years in the future. Lithium sulfur, I think, is more like 5 years in the future if our technology transfer is successful.
For those of people who were here for fluorine, you might remember that most of the people who were involved in the discovery of fluorine died from that discovery. Any other questions? Well, thank you for coming tonight. We hope you enjoyed our 16th installment of Everything Matters, Tales from the Periodic Table. I hope that you will come back to future Everything Matters. I also host another talk that's called Full Spectrum Science. The subject this month is color, making color. So that will be on next Thursday evening, I believe. No, that's Thanksgiving. Next Sunday at 1 o'clock and 3 o'clock. Thank you for coming.